Our work is titled The Latent Factor Structure of Developmental Change in Early Childhood, and this is by myself, Ben Stenhaug, and then Professor Mike Frank, and we are both at Stanford University. So fundamentally, we're asking, how do young children grow and change? And perhaps a little bit more specifically, we're asking, is child development a single unified process, or is it a host of different processes? And of course, there's been a great deal of work with regard to child development, a wide body of literature and a variety of theories. Perhaps most famously, Piaget proposed stage theories that child development happens in these distinct stages. More modern theories have suggested that different facets develop on their own timetable. And of course, child development is something most people have experience with. One example is Mike's grandma, who put forth that children either walk early or else they talk early, as if these happen in some sort of compensatory relationship. And so our aim is to consider these age-old questions and just try to come at a maybe slightly different angle and have a small contribution. And our angle is that we have access to this unique empirical data set on which we can fit statistical models and try out some new methods, which I'll describe. And in particular, our goal will be to understand the dimensionality of the data I'm about to tell you about. And so the data we have access to comes from Kinadu Incorporated, who is a developer of parenting applications. They sent out a survey or a questionnaire to nearly 2,000 middle-class Mexican parents with children from 2 to 55 months of age. And each of those parents answered 414 binary milestone questions about their child. So, for example, one milestone question was, can your child find objects on the floor? Yes or no. An additional question was, does your child babble to imitate conversations? Yes or no. And 414 of these milestone questions the parents responded to. To give a slightly more detail or broader overview, Kinadu thinks about these milestones as living within one of four groups, either physical, cognitive, linguistic, or social and emotional. For example, physical is the most common group of milestones. There's 180 milestones in the physical group, and one such example of a milestone is, can your child stand on their toes? So a first cut is to just look descriptively at this data. So we make a plot. Each point is one of the 2,000 children. The x-axis is the age of the child, and then the y-axis is the number of milestones that that child has completed. You can see that starting at 2 to 3 months, most children have completed about 50 to 60, maybe 70 of the 414 milestones. And then as we go up to, say, 3 years or 36 months, you see that children have reached on average over 300 of the milestones. But there's a pretty good amount of variation for any single age with the number of milestones completed. A 3-year-old has completed somewhere in between 275 and 400, let's say. And that's a pretty large amount of variation for children of the same age. And it's going to be one of the things that we focus on in our model. So our method is to fit a variety of item response models to this data set. These item response models are most commonly used in educational measurement literature, where students respond to tests. Here we have parents responding for children to milestones, but the structure of the data is the same. So a variety of these models, the simplest that we fit is a one-factor model, where the probability of the child having reached the milestone, let's say, can your child find objects on the floor, is a function of the student or the child's factor score theta multiplied by alpha, which is the discrimination or the loading of that milestone on that factor, and then plus some milestone easiness parameter beta. And so the easiest way maybe to think about these or to visualize these is to look at a graph like we've shown, where the x-axis is that factor score, The y-axis is the probability. And you can see that for this one, as soon as a child has a factor score of theta equals 0, it's about a nearly 100% chance that they can find objects on the floor. In the one-factor model, we sort of have to think about that factor as being general child development. But if we move to the two-factor model, now we have theta 1 being the first factor and then theta 2 being the second factor. And when we visualize it, let's put the first factor on the x-axis, the second factor on the y-axis, and then color according to probability. Now we can conceptualize of these factors maybe a little bit more interestingly. Maybe the first factor is the child's physical development, and maybe the second factor is the child's cognitive development. And maybe we think that, or maybe we check the model to see if can your child find objects on the floor requires some combination of those abilities. We're using a compensatory model here, which we found fit better than alternatives, where being low on one of the factors, a child can compensate by being really high on the other factor, for example. To give a little bit more intuition, let's look at the same graphs for a second milestone. Does your child babble to imitate conversation? Interestingly, on the one factor, we see this flat line, which means regardless of a child's general development, the lone factor in this model, they always have the same probability of having reached the milestone. You might wonder, why would that be? What we think is that child babbling is sort of a vague term. Children make noises. Any parent might interpret, most parents probably interpret that as babbling, sort of regardless of child development. So it's not a very good measure of how developed a child is. So we fit a variety of these models. I showed you the one and the two factor model, but we also fit a 3, 4, and 5 factor. And then we fit them. Exploratory means that the model can learn that any milestone loads onto all of the factors. Confirmatory, on the other hand, we say, okay, this is a physical milestone. And so we'll label this as a physical factor, and only the physical milestones can load onto the physical factor, and same for cognitive and otherwise. So we're specifying in more detail the structure in terms of a confirmatory model. When we're fitting these variety of models, what we're interested in is which model best fits our data. And the way we measure that is using a cross-validation procedure where I'll represent each sixth of the data as a child here. So the first 1, 2, 3, 4, 5 children, or the first 1, 2, 3, 4, 5 partitions, we fit the model to. And then that last one is out of sample, and we look at how well each model predicts that out of sample response. And we're basically judging the models, evaluating the models based on their ability to predict out of sample. And we did that for the sixth child, but we sort of rotate through doing what's called k-fold cross-validation as our model evaluation technique. So when we do this, we find that the exploratory 3-factor model wins, which maybe makes you wonder, why couldn't the 1-factor model win? Well, looks like based on the 3-factor winning, the structure of the data is more complicated than a single factor can pick up. You might then wonder, why wouldn't the 4 or the 5-factor model win? Well, maybe the structure isn't that complex. Maybe we don't have the data to find that nuanced structure. In any case, the 3-factor model is the one that wins in terms of the cross-validation procedure that we set up. To give just a little bit of intuition, we can show the milestone parameters for a few of the milestones. Find objects loads most on the first and the second factor, not very much on the third factor. Makes guttural sounds, loads almost not at all on the first factor, and a fair amount on the second and the third factor. So this starts to get you wondering, what are these different factors? And we look at that in a couple of different ways. We can graph, we can estimate the factor scores for each child, and then plot it according to their age. The first factor, unsurprisingly, but I think interestingly, is very, very strongly associated with age. So that makes sense that we can probably think of that first factor as being sort of general development that is strongly associated with age. The second and the third factor is not so much associated with age. So if you think about that variation between children of the same age having a different number of milestones, that gets encoded in these second and third factors, which I think is interesting to point out here. That's on the child side. We can also try to understand these factors on the milestone side by seeing, can you label them into groups? Well, which groups load more or less heavily onto which factors? These are high dimensional, these are complicated models to interpret, but the first factor, the milestones that load most highly are linguistic. Second factor, physical, is highest by a little bit. And then the third factor is back to being linguistics and is actually quite low on physical. So it's interesting to try to get a little bit of a sense of what the factors are finding there. Our takeaway was evidence three-factor model for multidimensionality of variation across children in development. And this begged a second question, which, okay, so there's multidimensionality here, but does this dimensionality vary by age? We're motivated here by the de-differentiation hypothesis of cognitive aging, that as people get older, the number of relevant factors decreases. Maybe there's the differentiation hypothesis of child development. As kids get older, maybe more factors are relevant, but at younger ages, maybe just one or two factors would be useful or relevant. We looked at this in two ways. The first is looking at where those models performed well. This graph shows is that above 10 months of age, the three-factor model outperforms the two-factor model. But at very young ages, it's actually the two-factor model that's winning. And so we take that as light evidence that before 10 months of age, actually simpler models, fewer factors are valuable or are necessary to model this data. So we take this as light but interesting evidence for that differentiation hypothesis. We also take a second approach at this question, which is where we partition the data based on age. And then within each partition, we do that cross-validation procedure. When we do that, we see that in the 2 to 12-month partition, a two-factor model actually performs best, outperforms the one and the three-factor. Whereas in each of the other older partitions, it's the three-factor model that wins in terms of this out-of-sample prediction metric. And so we again take this as evidence that for the differentiation hypothesis, that maybe for this very young children, the best model is just two factors, as shown by the top facet of this graph. And so, as I said, these approaches to us are tentative support for a developmental differentiation hypothesis, which we find quite interesting. Now, summarize the project, take a little bit of a step back. So we asked, is child development a single, unified process, or is it a host of different processes? First, we looked at this large data set, 2,000 children, 414 milestones. We compared a wide variety of item response models and found that a three-factor explanatory model best described the developmental variation. Second, we then looked at this developmental differentiation hypothesis, and using two different approaches, they both showed evidence for that hypothesis, in favor of that hypothesis. Obviously, there's a variety of limitations that should inform future work. The first, data is cross-sectional, so we're looking at variation across individuals, not within individuals. It's important to point out. Second, this data is based on parent report, which can have significant biases, of course. Third, our data comes from middle-class Mexican parents who use group care. Obviously, that's a very specific population. The results may vary for different populations, and we'd be fascinated to see that. Fourth, child development here is implicitly defined by Kinnedu's 414 milestones. We think they thoughtfully put those together. We think they make a lot of sense, but it is important to point out that at the foundation of this work is Kinnedu's definition of those milestones, and us taking that as the definition of what it means for a child to develop, marking off those milestones. And then fifth is with the nature of these models. So these item response models are, as it says, at best, a distant reflection of the structure of latent variables internal to the child. And we need to be sure that this is just a model that is useful for seeing the variation. It's not showing us anything sort of internal to the child. We don't want to over-interpret our models in that way. I'll close with a few acknowledgements. First, thank you to Kinnedu for their support and data sharing, both of which made this project possible. Also, thank you to a variety of colleagues and reviewers for their feedback, all of which significantly improved this project. And then third, thank you to the Stanford Data Science Institute for funding for my time and my energy on this project.